um, there would be some relatively difficult um, problems or questions, which would be still considered as some um, basic facts or like foundational facts, so that they're in the foundation of some area of studies. And they're considered to be known. So that is the situation with problem number 5A, for example. And probably 5B as well. So that would be a sort of effect, um, which would be quite difficult, but it's it would be dealing with some sorry. It's an interesting question. So the difficulty of this problem would be that it involves just very few objects, right? And still we have some non-trivial question. So the trick is that there would be some short solutions. But short solution, as you may imagine, and probably as you know from experience, is not always the most simple solution. I can even tell you a joke, though, like a story which is almost a joke, though it's not a joke, but a real story, and it's not very funny. So time to time, some countries, they try to, like, not countries, of course, but like some teams, particular teams, tried to cheat during IMO. So story knows about at least two such cases. So without naming directly, like both of the stories was when team leaders of the like of the teams um, and then like the procedure of selecting the final list of the problems was a bit more a bit different from now, and it was like more open, not meaning more transparent, like just all the team leaders or like representatives from more or less of all the countries, they had access to the meeting one night before the Olympiad. So they technically knew the problems. And there were at least two occasions when team leaders decided like to help to the competitors, and they passed passed them um, a solution of just one problem. In both situations, it was just one problem. They thought that it would be sort of invisible, like that they just give short, relatively easy solution, and like no, like the guys just write some simple explanation, and that's it. Like nobody can tell that something wrong happened. But the fact was that in one situation, like those, I believe, like all of the team, like six, maybe five competitors, they wrote the solution, and they became like more or less the only people who solved the problem. Maybe one Chinese guy was also like had also solved it. Other time it was like very comparable situation. So like the shortest solution became actually wasn't absolutely an indicator of easy problem, right? So I would compare this situation or refer this situation to some of these problems. So they admit some easy solution, some like meaning it is short and understandable if pronounced. But for me personally, problem number 5, like it gave me a hard time when I was solving it because it was too unusual, right? So if you train on such problems, they become less unusual for you. You get familiar to some additional tricks. Then after this process, they wouldn't be considered of, I would say, IMO level. But if you never touched that tricks, then it would be quite comparable because it would be new and like probably 30 years ago, something comparable to that may be on IMO. Like not 30, but maybe 40 years ago, like it could happen. So it's not a direct answer.
Thank you.
Not at all. Okay, let's start. We have quite big plans for today, at least I have. So first of all, we will have also sort of a repository for the tasks. Like it was a bit complicated, like my schedule was a bit complicated this week, so I didn't manage to do that, but hopefully I will do that on the weekend. That is the first announcement. So we will go through some of the problems now. I will tell the solutions, or at least some ideas. But for some of the problems, we will not touch the solution, just because if we try to discuss every problem in class, we'll have rather less time for new topics. And that is basically that is the style of my preparation when I was school student. Like solving all the problems, like not solving, but discussing all the problems from a list on some particular topic in one class, it's normally an excessive practice, though some trainers still try to do that, but they definitely lack time all the time. That has some practical implementation. That means that everything which was not discussed in class remains still your home task. So I expect you to try to solve as many problems from my tasks as you can without any additional notice. So like every new problem, especially a hard one, is your chance to practice more, to train more. Okay. So let me start from the problems which I remain to you to the home task. So there was a problem. There was the first problem of the home task. I believe it caused not so many not so much troubles to you. So I will probably skip it for now. But like if somebody needs some clarifications there, you just let me know later, and we will start from the second problem, which was discussed, the hard one, the one from IMO. Okay, so this was this was the picture, right? The starting picture. So what I announced is that we can divide the problem into two problems. And like the division became somehow natural if we considered sort of the sort of dynamics in the problem. So as points D and E are chosen arbitrary, like with preserving just very basic property here, so that D and E belong to namely these lines, and the lengths here AD and AE should be equal length. Should be just equal the lengths. So we still have freedom to move D along the segment, right? So that is how we came to the idea that probably we can study what's happening here, like as no clear idea emerged immediately, how to approach the problem here in general case. The natural idea was to try the situation, the problem, with in some particular case, which would be still relevant, it would be still challenging, but probably more doable. And such case seems to be the situation when points E and C just coincide. So we have this picture, and as I noticed earlier, we need to prove that angle ACD equals to angle ABF. Why is it true? Just because of the angles denoted here. So these two blue angles would be equal because this is an isosceles triangle, and here DFB would be also a isosceles triangle. So the green angles would be also equal to each other, and we need to prove that FDC would be the same straight line. So that would be perfectly enough to show that these two angles are equal. If so, we then have that the angles here would be vertical, ADC and BDF. As then like enough to prove this, as then angles ADC and BDF are vertical, as side AB is common for them. So this is sort of a standard trick when we have common side for two angles which are about to be proved to be vertical, and we need just to prove about the other two sides. Those actually form a straight line, and that is what we're about to do. I will also have some comment later on this logical trick or logical line of reasoning. So now we may focus just on this fact, which looks rather more elementary, at least for me. So how can we approach this angle counting? But actually, this question is rather basic. So if we denote angle A to be equal double alpha. Why I do double alpha? Because we depend here on the bisector, angular bisector. So it would be rather more convenient to me to two alphas instead of using alpha over 2 all the time if I denote with one letter the entire angle. So it's just convenience. So I write then these calculations. This angle we can actually skip because I like observing these situations in the following way. So we fell down into sort of a different sub-problem. So we basically have another picture, like more simple probably picture here. So we have something like this to focus on. No, like it doesn't give us any advantage not drawing this, but still. Okay, sorry. Not here, not in this problem. So we can calculate that this angle would be equal to 90 degrees minus alpha. And what we can do from problem number 5 is that yeah, so like here the hint that 5 is auxiliary for problem number 4, which was marked in the beginning of problem number 5, is quite substantial because otherwise we may get in some troubles by like drawing excessively complicated picture if not using that fact. So we do instead the following thing. So we consider the point so what is stated in problem number 5 that we need the external angle here, external angle A, and we need its angular bisector. Something like this. Like there would be some methods how to skip this on this picture, but they would be normally they would be more tricky. Just one moment, I will double check if I remember any rather more simple. No. So we can like in problem number 5, we consider this external angular bisector over here. And the statement is it passes through point X so that problem number 5. Sorry for the jumps. So we need to prove 5A. We need to prove that arcs CX equal to XB, where we consider by arcs like arcs over here. probably we rather draw it on the next page. Okay, but what this condition means? Actually, this condition means that we must have equal chords here, right? And here, I want to make another sort of intervention. So, as last time I mentioned this approach about objects, properties, and relations. Now I want to recall one other principle, which I believe to some extent is very familiar to you, but most likely not all of you use it, I would say, to the full extent. I call that principle of blue fact, red fact. Like the title, first of all, it's not very official. Like it's absolutely not official. Secondly, it's the title is referring to some other, I would say, proven techniques. So it may be not clear why this title is chosen, even after I will pronounce the statement. So don't be surprised. And like if speaking namely of the principle, then we use sort of color diagram or color differentiation of facts. We sort of color them. We say that red fact is a statement which is true, which is why it's called, we call it fact or refer to that as a fact. And which is already proved or verified. Why I say proved or verified? Because some facts, some statements we don't prove, but still we get them being usable in the valid way, because sometimes they are part of the conditions, sometimes they are part of some assumption. For example, in the assumption of contrary fact in proof by contradiction, or in induction assumption. So there are several methods how we can get fact being sort of labeled as verified and good to use. So this one is like these two dimensions. The statement itself is true or very likely, I would say very likely to be true, which is 100% likely here, and already proved. Blue fact, on contrast, would be a statement which is with a high probability informally. like speaking informally here with about high probability, like with good chances or with some good reasons, real I would say real world reasons why it should be probably true. But we still don't have valid explanation for that. Like valid mathematical explanation. So this is a classical issue for those who just start doing mathematics, that they just don't understand the difference between red facts and blue facts. One of funny stories when students just start proving something, so which is of course not the case for us, but just to understand what do I mean here. Like some students which just start these proving techniques or proving studies, they don't understand what exactly to prove, because normally they are used to problems where they need to find the answer, but if they already have the answer, like it looks for them that it's already done, right? So in other words, if a textbook has a problem which claims prove that this angle equals to that angle, for such students, this is like a given uh, a given fact that this is true, because like it's printed in textbook, in official textbook, it claims the result. So what else like people do need here? Of course, we realize the issue with this line of thinking, but this is, I believe, quite classical explanation. What is the difference between blue fact and red fact? So by the fact that the problem was printed in textbook, we somehow understand that most likely the fact would be true. Like not the like it's not a fact so far. It's a statement. It's claim, right? Fact is something different. Fact is when we know the event, when there is a sort of event and we know that it happened. So the observation that we can like the observation that it happened is the fact itself, and the statement would be description of that fact. So from this point of view, the problem which is printed in a textbook or some clear statement is not a fact by no means. It's just some statement. But that is why I call it blue fact. So if it would be rightfully proved in mathematics, then in mathematics it becomes almost a fact, right? So we just show that it really happens as it is, and like in mathematics is as mathematics is not physical discipline, it's like more virtual discipline. Like the fact in mathematics, like it's more or less everything which is proved. Like it's not very strict division, but like still. So in this language or in this slang, we can reformulate our purpose for each particular problem. So in most problems, like for now, we have the answers, right? We just need to prove them in most of situations. So like at this level of mastering mathematics, there would be rather more problems with the answer already known. So our purpose is actually to convert this blue fact into red fact. So this statement which was not good to be used, to convert it to the state when we may use it, and to convert it in mathematical manner, of course. So what is the use of these just two fake definitions? So these are not real mathematical definitions, as you can notice. But the thing is, we can do sort of planning or strategical planning, not strategical, but tactical planning, like step by step, by using this division as sort of a compass. So here, for example, if we say that we need to prove, like, once again, this symbol, this is just substitute to the word prove. So if we speak of proving the statement of the problem, it may be reformulated so that we have a blue fact that the arcs CX and XB, the smaller ones, they're equal to each other. This is blue fact. So if it was true, then actually we may say conditionally, that means with this preliminary condition, we would have that CX is equal to XB, right? So it also becomes blue fact, which was illegal before, becomes sort of also usable, but just with slightly different rules of usage. So we may imagine that we can use this fact, and we can try to find the consequences of these observations. And when we look for the consequences, that is sort of inverse logic, which is not true in mathematics, right? But we still may have some use of that. So if this was true, then we would have another blue fact that, like the reformulation of this blue fact is that CX is equal to XB, so that it's like isosceles triangle, right? So another blue fact would be that angle XCB is equal to angle XBC, which is also sort of a fact, like this statement must be true if the problem was true. But by no means it's the proof of the statement. But here is the miracle. Sometimes we can prove this just independently from this from this trajectory. So now we can say, hey guys, like this was just a situation with circumcircle and some inscribed angles. So we may say that, but angle BCX is equal to angle BXA. BCX, so these would be the same angles, right? And on the picture, that would be just equal arcs. That is why this language is very useful. And
it should be BAX, right?
Sorry, come again?
BCX equals BAX, not BXA.
BCX, BCX, sorry. BAX. Yeah, that's correct. Thanks. BAX. Yeah, that's right. And now we realize what we want to do. We want to show that it is really true that this angle, so we already suspect that, right? Because of this invalidly proved, but still like some people would say proved observation. So we want to show that this angle is equal also to green arc. And we have actually a number of ways to do that. So for example, and from cyclic quadrilateral AXBC, we have that angle XBC equals to, and we have like different options here, how to like what to write. Angle XBC plus angle XAC would be equal to 180 degrees. That is the widespread property, like the most famous, one of the most famous properties of cyclic quadrilaterals. But actually, I like reformulating it in slightly different manner. So angle B equals to external angle A, or in like more precisely, angle XB XBC equals to angle XAM, with notation where M shows the direction of the ray. But this is also a green arc. So what happened here? We really proved here this fact, right? So we have that from this quadrilateral here, AXBC, this angle equals to the external angle A, means to this angle A, or more traditionally, this angle B and the angle XAC, they sum up to 180 degrees. So angle B would be equal 180 minus XAC, which is exactly the value of the external angle XAM. So we have that this angle here equals to one green arc, which is same as one green arc here, because this was the external bisector. The green arc over here is namely angle XAB, which equals in its turn to the angle XCB, because of just, I don't remember how it's called, like bow arc property or something like that. So like one of the basic properties of inscribed angle. So this inscribed angle equals to this inscribed angle because they have same underlying chord of the same circle. So eventually we made this, we recolored this blue fact to red. May we say that this statement becomes red automatically? Absolutely no. Like there is no automatic spread of this like proof in the inverse direction, right? These were rightful logical arrows. So this is an implication of this. This is an implication of this. So the logic went that way. But sometimes the relation would be relations of equivalence. So here, for example, we namely have such a situation that we have a triangle, and these properties of isosceles triangles, they are equivalences. So these two sides are equal if and only if the two angles are equal. So we can reverse this logic here for this step. And for this step, we also can do that, probably with some additional, nodes. So here, some additional nodes may be needed because we have two arcs which are bounded with the same chord, right? So that means actually that we may be in need of considering the sizes of the chords. We must notice that, okay, this arc couldn't be like if we have two equal arcs, or if we have two equal chords and we compare two arcs here, they may be either equal to each other or they may add up to 360 degrees, right? To the full angular measure of a circle. So this is why it's not equivalence that we want to consider here, the step here. But by saying that, okay, we cannot have these two arcs being added up together to 360, because after considering these two arcs, we have another arc remaining. So their sum is less than 360. So this opportunity is not realized in this situation. So we will actually have this being true. So here we have both things. So first, we actually considered what are blue facts, like the concept of blue facts, red facts. They are one of the possibilities to choose and to make some strategy how to approach some statement. So you suppose the statement is true. You then try to find as many consequences or implications of this property as it's possible at the moment. And then when you do that, sometimes you may find another proofs of some of the implications, and somewhere you will be able to inverse the logic of proof. But also what we've done, we actually proved just the problem 5a. We also will need problem 5b. Any questions so far? Okay, seems like no questions at the moment. So problem 5b. So basically we will need the same picture here. So in this problem, we need to consider this strange construction, this broken line bisector. and we consider broken line seems like there was a typo here. So we need broken line CAB actually. So we need this CAAB. Sorry for like inaccuracy here. You can set the broken line bisector for the broken line ABC. No, like we need CAB because we need this point. Yeah. CAB. So we here. Сейчас занятие ночью. Нет, не заглядывай, пожалуйста, да, не с учеником, там большой класс. So, like how we can approach this definition of broken line bisector, first of all, like we need to find the midpoint of the broken line. And finding the midpoint of broken line. Малыш, не надо, пожалуйста, там не человек, не отдельный человек сидит. Пожалуйста, не заглядывай, у меня сейчас работка. Хорошо. Хорошо. So we may consider the following construction. We know that AB is greater than AC, so we consider here point A prime, for example, so that the segments would be equal AC and A prime B. So A prime, a point on AB, so that on segment AB, so that A prime B equals to AC. Then finding midpoint of the broken line becomes a rather more simple task because we have two equal sides or equal segments on the ends of this broken line, right? Starting from C and starting from B. Same segment is measured. So we now take just point, say, P. P would be point on the segment A prime, like P would be midpoint of A prime. So actually this even is this notation is probably a bit excessive. So now we can consider the triangle AXA prime and the midpoint here. And you can notice that actually this picture becomes somehow similar to this picture, or this picture. So we just had the segment here on the different end. And we need to prove that we need to prove that XP is perpendicular to AB. So prove that XP is perpendicular to AB. Which would immediately mean, so again, speaking in these terms of red facts and blue facts, this would be followed with a blue fact that this is the triangle AXA prime is such triangle that a median XP would be also a height So it would be like from this we can deduce that ax a prime is how it's I don't remember how to spell it. So it's isosceles triangle. But here would be a rather more simple situation because it would be actually an equivalence, because there is this famous property that isosceles triangle is no, not like this. That in a triangle, median and height coincide if and only if it is isosceles. And this segment would be also a angular bisector, angular and orthogonal bisector of the same triangle. So this would be like, we can express this without these blue facts and red facts, but we actually we may realize it later on, that it's not just blue fact, it's sort of equivalent fact. For me, it's rather more convenient to expect from myself that I first find some consequences, and then I'm sort of making some strategy how to reverse the logic or the logic line, instead of sticking up with just equivalences in such situation. So even if it was not an equivalence, I would try to use this. So here we end up, like, not we end up, but we now consider this statement rather than the initial statement. But this becomes also something doable. So if this is so if it is isosceles, then we would have that these segments should be equal. We also have these segments being equal, and we just proved recently in the previous part that these two sides are equal. So we basically have that this would be, I would say that it gives us another blue fact, but actually we can say that it gives us another equivalency, that this would be equivalent here, but equivalent in our some strange understanding that we can do that in this way, and we also can do that in opposite way, but probably not with the same statement, not in the same step. So we can say that it's equivalent to triangle AXC being congruent to triangle A prime XB, right? So we have this virtual equality of these two sides here, which is still not done. But if we have it, we would have this side property of triangles, by which we will have congruence of the triangles. So now the question is how to reverse this line of reasonings, which is not valid in traditional sense. But now we can easily prove it, but it's true because of other three elements. So we have XC being equal to XB because of 5A, right? We have AC equal to A prime B by definition of A prime. And we need just one more angle here. So angle XBA equals to angle XCA by cyclic AXBC, right? So we have this angle being equal to this angle because of the same underlying arc. So that's it. Like that would be side angle side property. So this becomes red. As we have these two triangles being congruent, then we have that these two sides being equal naturally. So it also becomes true. It becomes red fact. And if these two segments are equal, then we have that the triangle AXA prime would be as this one is isosceles. Then the median XP would be also a height. And that is exactly what we needed here. So we recolored this statement as well. So this is how this strategy of making logical lines really works. So that is why I like it so much. We start from something almost illegal. Speaking of traditional mathematical lessons, I wouldn't say this is something revolutionary. Like it's normal process of research. So that is what an average researcher, like professional researcher would do. Like they would study something like this. But this is absolutely not in line with what oftentimes is taught in schools, in like traditional ways to approach geometry. Okay, so finally we have both parts of problem 5. And that's how we actually know some new property here on this picture. So we can then do the following trick. We can denote point B prime here. So B prime is a point on the segment AB, so that B prime B equals to AC. And then we immediately come up to this situation. So we may consider the midpoint of the broken line, and we may consider the orthogonal bisector here, or perpendicular bisector of this smaller segment, and also that would be, as we saw, it would be a midpoint of the arc BAC. No difference which exactly way of presenting the construction you choose. Like that would be still the same construction, right? So here we have this point, I would call it X. And we have all these interesting details from the previous problem situation. So we have, first of all, this. We also have, we may be interested in extending the line. But probably that's it. That's what we need. So we know that this would be external bisector. So this external bisector, it would be related to the same point X as this intersection point of the orthogonal bisector of this segment and the circle. But we have same situation here with the segment of the same length, right? We had this equality that AC, the lower side, it was equal initially to AD. So we have that B prime B equals to AD. So that is basically how we have some symmetry related to the segment itself, but also to the circle somehow. So if we consider the bisector of the entire chord AB, which definitely passes through the circle center, we have just symmetrical situation. So we have that points. So we consider let L be let L be the orthogonal bisector of the segment AB, right? And then the circle is symmetrical with respect to the line L. Or symmetrical at L. Why is that? Like one of the basic properties, so like the orthogonal bisector of any chord passes through the center, and like the circle would be symmetrical in any straight line passing through the center, right? Then A and B would be symmetrical at L. Why is that? Just by the choice of L as its orthogonal bisector. But also we have that B prime and D would be also symmetrical in L. But that is how we can observe that. So the orthogonal bisectors to AB prime and DB. So these two segments, they're symmetrical to each other. So their orthogonal bisectors would be then also naturally symmetrical. Also symmetrical. So X and F are also symmetrical at L. Why is that? Because we have some symmetry, like reflection symmetry, right? Or mirror symmetry, so that it with regard to this symmetry, one straight line and another straight line, the orthogonal bisectors considered here, they are symmetrical to each other. And we have the circle which is symmetrical to itself in this symmetry. So the intersection point of one straight line and the circle would be like if we do the symmetry, they would be mapped correspondingly to another straight line of these two and to the same circle. So the intersection point will be mapped to, or will be sent to another intersection point to the F. And F just similarly would be sent back to X by the same reason. So we have that X and F would be symmetrical with respect to this straight line. So XF would be perpendicular in in particular, XF would be perpendicular to L. So XF would be parallel to AB. And this is what we actually need. There would be some other ways how to prove this, of course. But I believe this one is most geometrical, and at least this one is very geometrical and very visual. Still not very difficult. So what we basically needed, and what we've got now is that we have this straight line being proved to be parallel to AB. And now you can and just not to forget what we are studying here, what we want to prove. We want to prove here that the angle FBA equals to the angle ACD, right? We know that actually we almost approached that because of this geometrical observation, we will naturally show that both of them are equal to this red angle here. So we can see, we can now complete actually. So now we have the following thing. We have that one blue arc plus two blue arcs would be equal to 90 degrees, right? Just because of the triangle DAC. This would be side angles and half of this angle. But also two blue arcs plus one red arc would be also 90 degrees because this would be internal and external bisectors. So from here, we conclude easily that one blue arc plus one red arc is equal to 90 degrees, right? So what we now want to show after all this we considered here, we want to show that one green arc is equal to one blue arc, but that is same as saying that one green arc is equal to red arc. But because of this symmetry, it becomes very trivial because that would be side angles of a cyclic trapezoid, right? XFBA would be trapezoid. So we can say that AXFB. AXFB is cyclic trapezoid. So its angles XAB, XAB, and FBA are equal, which is just the same as saying that one red arc is equal to green arc. So we finally have, that blue arc equals to red arc equals to green arc, which basically we need it. Which completes the proof of the first part, right? So we proved as we announced before, that was enough for proving that points F, D, and C belong to the same straight line. F, D, C belong to straight line. Let's have a small pause, after which I will complete in more or less fast manner the problem here. I will tell one more solution of maybe a couple of solutions of the problems of the previous task, and I will announce some particular features of the next task. But in principle, these blue facts and red facts, this concept in different implementations, it was almost like the main part here, like of today's class. So we just need to put more particular facts, like geometrical facts, for today, so that we cover the entire program for today. So let's have a break for like 4 or 5 minutes, and then we continue. Okay, 1, 2, 3, 1, 2, 3. Can you hear me, guys? Are you here?
Yeah, you sound clear.
Okay. Any questions so far? Okay, so one side note is that mm, um, I want you to realize that simple looking, like the way, just in principle, the process of solving a problem and process of um like reading the solution or getting used to a solution, that would be two quite different two quite different actions, two quite different skills, um which need absolutely different characters from you. So when I tell you a solution, probably the last thing which I want from you is to remember the solution itself. I really want each solution I tell you to be a motivation for your deeper thinking in some direction. I believe that just going through many solutions with some other people, probably the most experienced teachers and trainers possible, it's still weaker training than just doing half of those problems but yourself. I don't know. Somehow it works like this. Like it's feature of our world. Um, that probably means that you should appreciate that moment when you have some questions regarding to some solutions or ways of thinking. I realize that they come not all the time, like some reasonable questions, but each time you will have a question, I would be happy to answer. Okay, let's go further. There were several quite different problems, so I actually wanted to discuss two of them. So first, there was problem number 4, which is quite useful. So I really applied it in several situations, in like on some Olympiads. Not here. Just one sec. So actually, in this problem, it's more a joke, this reference to some ellipse, because we will use just metrical equality from this. Like we wouldn't use any properties of ellipse other than just the definition. So this basically would be a problem about just lines and about lines and tangent lines to a circle. So as normally we start from a picture. On the sides, AB and BC of triangle ABC. A, B, and BC of triangle ABC. Points D and E are chosen. D, E. Segments A, E, and C, D intersect in some point. Point F. Prove that a quadrilateral DBEF, so this one, has an incircle or is circumscribed, I think it's called, if and only if points D and E lie on the same ellipse with foci A and B.
It should be A and C instead of A and B.
E and C, yeah, that's true. So there was this correction, right? So what does this condition say? Like, it says, if considering directly, it says that there is an ellipse with this foci, like foci is plural for focus. I hope this didn't how to say it, prevent you from understanding. Just what's that? Greek, right? Greek form of a word and Greek word. But technically, there is no use in this deep understanding of that this is there is an ellipse of this fashion which passes like has foci here and passes here. Basically, that is just an equivalent statement to say that AE plus EC equals to AD plus DC. That's it. So prove that the circle here, prove that the circle here exists if and if only we have this condition satisfied. And now, after having this draft sketch or draft picture, we can try to find some strategy how to prove this. So what happens to many of such problems when we need to prove that some circle is like has in circle, some quadrilateral have in circle? It's quite difficult to approach geometrically this property. Sometimes it's doable, but not that often. So the very classical example of such statement is that a quadrilateral is tangential or circumscribed. Let me find proper wording. Just one sec. Yes, that is like circumscribed quadrilateral is also applicable. So suppose we have a quadrilateral, which is either circumscribed, or we just want to study if it is circumscribed. So the condition of being circumscribed, by the way, who remembers? Like, let me know, please, if you remember what is the condition for a quadrilateral to be circumscribed. Like, just on the chat, either raise your hand here on Zoom, or just write something to the chat that you remember or you don't remember. So, okay. Okay, so like the condition here would be that AB plus CD, like ABCD is circumscribed. So if and if only AB plus CD equals to BC plus AD. So that would be like natural and like the most famous condition, which we are not going to prove. So if you don't remember this, or even if you didn't know this, you can easily find that on internet. Dislike this problem, for example, it would be rather more rare. So what we can notice, what is common for many such problems, is that direct geometrical approach to them may be quite troublesome. So we have very special relation here, that some geometrical property is related to metrical property. These oftentimes they are indicator that the proof would be quite technical. Actually, for most of these, good idea would be following. So strategy here, also related to these blue facts and red facts, and also to the strategy of moving the points. So the strategy would be like first proving geometry to metrical. So the difficult part normally would be going from the equality to the geometrical sense, and here as well. So going from this equality to the fact that the quadrilateral is circumscribed. But rather easier part would be going from geometrical side to metrical part. So that is how we come up to the idea that let's start from assuming that this is circumscribed quadrilateral. And we do study this in this case, like the situation. And actually, in this direction, it would turn to be not very difficult problem. So we have this A, B, C, D, E, F, D, E, F. Here I would use slightly special technique, which I believe you should be familiar with, according to some previous notes. So like from your notes or notes of your trainers, like from some previous trainings. So I would compute this compute this segment. I would call this tangent point being point T. So I would compute BT from triangle ABE. So BT equals to AB plus BE minus AE over 2. So if we consider this triangle and we consider its incircle, then the tangent segment from the vertex to like to the tangent point of the incircle would be calculated as half of sum of the neighboring sides minus the opposite side, if we speak of this vertex. So similarly, if we consider BS from triangle BDC, we have that BS is equal to in this triangle, the neighboring sides would be AB and B. ABE. Sorry, no, like BDC. Here, like the neighboring sides, BD and BC. So BD plus BC and minus DC, the opposite one, over 2. Like, of course, it's not an arbitrary choice of the sides. Like, this choice would come after trying some options, but in principle, that would be one of the first things I would try to do if we have incircle and sort of combination of triangles and quadrilaterals. No angular data here, like we have neither any angles nor any equal segments. So no signs of equal angles anywhere, just metrical equalities. I would try to get use of this representation. So by the fact that these are tangent segments to the same circle from the same point, we have that BT should be equal to BS. So we have this equality that AB plus BE minus AE over 2 should be, not should be, it is equal to BD plus BC minus DC over 2. And I would emphasize that it is equality or verified equality. I would put an exclamation mark that it's not under question. It's like something we know here. If it's circumscribed. And now we do some simplifications and we try to realize how far is that from what we need. So we need we have here that So we have that AB plus BE plus DC would be equal here to BD plus BC plus AE. So I just drag this to the other side and DC to the other side. And what we need, so this is what we have. What is questioned is AE plus EC. I will write it in different order. AD plus DC equals to AE plus EC. Why I did write this in this manner? Because AE is same here, DC is same here. AD is somewhat related to AB, right? It would be part of AB. As well as EC here would be part of BC. So we have some arithmetics hidden here. So from what we have, I would change the representation to AD plus DB plus BE plus DC. Is it equal to, sorry, it is equal to BD plus BE plus EC plus AE. So we need here AD and DC, and we need here AE and EC, and we need to prove that these two terms equal to these two terms, but we indeed have that, right? So this would be just the same as here, or more precisely, this is cancelled with this, and this is cancelled with this. So that is exactly what we needed. So actually that finishes the proof in one direction, right? And what we need the proof in the opposite direction somehow. But now we will have no geometry. We will have just metrical equality. But there would be the trick which will help us. So if let's start from another page. If we start with the equality, then we have that AE plus EC, AE plus EC equals to AD plus DB. We have the similar picture. A, B, C, sorry, D, C here. D, E, point F. And we then do the following. We do inscribe, like we consider a circle, but which would be the best fit in this situation. So it's most likely would be not perfect fit for us. So we consider a circle which would be inscribed to one of the triangles, for example, and wouldn't be inscribed to other triangle. So we consider circle omega inscribed to triangle ABC. Oh, sorry, not ABC, DBC. DBC. And then we do sort of fit the situation to the geometrical part of this problem. So I do consider a tangent segment of the same fashion. So I will call this point E prime. Then we can say that by the first part of the problem, we have that, like here, I would specify what is E prime. So let E prime, point E prime, be a point on the segment BC, so that A E prime is tangent to omega. Then by the first part, actually this construction of points of the triangle ABC sorry guys, one sec. Something wrong with the charger. So if we consider a triangle ABC points D, E prime, and the circle, we get exactly the construction from the first part. So by the first part, we have that A E prime plus E prime C equals, and this is not under question, this is what we have, equals to AD plus DC. And this looks a bit like induction here, may look a bit like induction. So we have, we can rightfully use part of the statement which we prove, right? So in this situation, we have found this moment when we can use this. But also, we have that AE plus EC equals to AD plus DC under the conditions. Right? So we have that AE prime plus E prime C equals to AE plus EC. This is quite classical situation. So we have the same expression, metrical expression for a point and for the shifted position of the point. And this is where we actually touch the topic of the previous class, like these shifts of the point, shifts of some structural elements. In the previous problem, we saw quite a different manner of shifting. So we were freely shifting an object. So we consider the dynamics of the situation. Here we have a different sort of a shift. We have some metrical property to keep an eye on, and we sort of we have this statement. We have a promise by somebody. We can imagine that we have a promise by somebody that for the shifted position of the point, we have the same metrical property. And what we need to do here is actually to show that the condition is so strong that the shift, there is no possibility for a shift, that it's not possible. Here, in particular, we can use quite simple technique. So, like, without loss of generality, we can assume that E prime belongs to the segment BE, right? Like, one of them would be closer to B if those are two different points. Then we have that AE prime plus E prime E plus EC equals to AE plus EC, right? So this is just E prime C. But then EC is crossed out, is cancelled from both parts. So this would be equivalent to saying that AE prime plus E prime E equals to AE, which contradicts contradicts to triangle inequality. To triangle inequality. So it's just impossible, right? If E is different from E prime. And like quite trivial if they coincide. So this finishes the proof. And actually there is a number of statements, of geometrical statements, geometrical properties, which would be proved exactly in the same manner. You will have several of them in your next home task. Some of them would be quite useful, for example, for some technical purposes, like some numerical techniques would be based on such properties, which would be proved in this manner. And what like the last thing which I wanted to mention, we have just short time remaining, and I need to finish on time today. I want to discuss, to still consider the problem 7a about the circle and the tangent line, because that would be, first of all, that would be something quite basic for circles, which you know even without this problem. But on the other hand, is that with the same method, you can prove that for like you can use the similar trick for the ellipses, the 7b problem. So what we have here, we have that there is a circle. There is the center O. And we have definition of the tangent line as a line which has exactly one common point with the circle. And we must prove that it is perpendicular to the radius. And this is somehow, it oftentimes go almost as definition of tangent line. So there is some, like, there is oftentimes some sort of a gap in understanding or in proof why tangent line in this definition is orthogonal to the tangent line. So geometrically, it's not very clear why, like, having just one point, like I mean geometrically from the point of view of proving, not from point of view of some obvious observation. So we can say that, okay, the picture is symmetrical or must be symmetrical. Just one sec. Just one sec. Яруш, если ты будешь так разговаривать с мамой, то ты будешь наказан сидеть дома в комнате просто. Чтобы я не слышал, что ты с мамой разговариваешь. Ты понял меня? So, like there is some hidden part here normally. So it's not that clear how to get use of this symmetry or whatever if we have just the fact that we have one common point. But then we can come to somehow similar, something reminding probably the previous problem. So we may suppose, like we may study first the geometrical sense, the geometrical part. So we observe here the equality of the angle to 90 degrees as something more metrical, right? As the metrical equality in the previous problem. So let's consider no, sorry. Like just vice versa. Here it's not that trivial what is like more geometrical, what is less geometrical. Here it would work rather like what is the easy direction of proof and what is more complicated direction of proof. So if we have here the angle of 90 degrees, if the angle is equal to 90 degrees, then what? Then actually we can observe easily that any other point P would be forming distance OP, which is more than OT, just because. Just one sec. Нет, отсюда я могу уйти в любой момент. Не знаю, ты мне не сказал, что я вам не тут мешаю. У меня занятия практически до 2, там, с перерывом, или даже до 3. С каким-то там перерывом в какой-то момент. So, like as it is hypotenuse, as OP is a hypotenuse. So we may like it finishes the proof in this direction, but in the opposite direction, we may consider like sort of the skew case, like of the position. So we understand that this is there is an orthogonal position for some line which is like also tangent line. So we know about this line that it would be tangent line because it would be having just one. Like why it is end of the proof? Just because as the distance is larger than OT, so which is it is larger than radius, so it would be further than the circle points from the center. So here we understand that this line, perpendicular line, would be already tangent line, but the question is why there is no other tangent lines here. And what we can do then is, considering any skew line here, so this would be already shift not of a point, but shift of a straight line from this point of view, like in the concept of the previous class. So it would be shift of position of this of the line, and then for this position we may consider so what we cannot use the drawing, right? We cannot say that there is an intersection point, because what? Because that is what is implicated from what is implied from the drawing, but we cannot use drawing as an argument, because drawing is not a logical structure. We, like in geometry as well in is mathematics, we may use some implication steps as arguments, probably conditions like from the task as arguments, but not the drawing, because it's not a statement, for example. So here we know that L prime is tangent line, and L, assume L is a tangent line, and L is not perpendicular to the segment OT. But then we may consider something to this construction. So, for example, we may then construct a perpendicular to this line, because this is a skew line then to the L, to the line L, like OT. It wouldn't be perpendicular to L by this condition. So the perpendicular, which definitely exists, would be some other line, OQ. But then let OQ be perpendicular to L, so that Q is belonging to L. Then consider point S such that Q is midpoint of ST. So here would be some point S. And then we can easily show, then we have that TOS is isosceles triangle. But then we have that OS is equal to radius, and then we have that which is impossible, right? Which is contradiction. So this is how we get contradiction. We do, for the shifted position, we do consider the geometrical properties of that situation. If we need, or if we can, we probably relate to the previous case, like to the direct case. If we cannot do that, like we just look for contradiction on the picture itself. So that is it for today. If you have any questions, please write me on WhatsApp. I saw that like you send me several messages which I haven't answered, like during like we just send me today. So like just keep in mind that it would be deep night for me because of the time difference. So I will answer them a bit later now. And I will send you the new list of problems, which would be still related to angle chasing and also this, I would say, shifting thing. So when we shift a point, when we shift a straight line, when we have sort of direct geometrical relation, like some geometrical property and then metrical outcome, but not clear strategy how to prove that in the opposite direction. Any questions now? If no questions, then we finish for today and see you next time.